This will be our last day on the fundamental theorem of calculus. So you've seen the two different parts of the fundamental theorem. One is when you evaluate an integral, and you have f of b minus f of a. And then you have the other when you take the derivative to get rid of an integral, both ways. So both have to do with getting rid of the integrals, just what's the appropriate step there to do for that. Okay, so we're going to use those two parts of the fundamental theorem to solve for various variables. So in this first example, we are going to solve for y. And we are also going to find c. Okay, so solve for y. And we're going to find c using the initial condition of 8, 0. Because you always have to have what's an initial condition in order to find c. Or you have to have bounds that get rid of c. But we're going to solve for y first, and then we're going to find c after that. And we're going to do that using the fundamental theorem. So this is what we're given. Given dy dx equals e to the x times the tangent of x. Okay, this is a product. In order to take the derivative of a product, what rule did you need? The product rule. Okay, in order to take the antiderivative of a product, you also need a special rule, which you don't know yet. And so we're gonna, I'm gonna show you how to do this symbolically, and then later we're gonna learn how to actually do it. So let me show you what I mean. We want to solve for y. That means get y by itself. Where's the only y in the problem? Okay, dy is the only one. So first I need to move the dx. If I'm going to get y by itself, I need to move the dx. So my first thing would be to separate the dx to the other side. So now I've got all the things that are parts of x on one side and all the things that are y on the other. This is called separation of variables, where you're just cleaning it up and so that the variables are all on the separate sides that they need to be. Okay, what's the only thing standing between me and having y be by itself? Okay, the d. D is called a differential. What's the only way to get d alone? Okay, so to get d alone, you throw an integral in front of it. But if you do it to one side, you have to do it to the other. On the left side, an integral and d, which is derivative for differential, cancel each other out, and we have y alone. On the other side, we do not know yet how to do e to the x times the tangent of x, because I haven't taught you the antiderivative for the product rule yet. So you're going to have to leave it e to the x tan x dx. But what you are going to have to put is that we do know that there will be a plus c on here. And it's going to have to start at sum a and end at sum x. Okay, we don't have bounds specifically. All right, what is the a going to be? Bless you.
Thank you.
You're going to get the value of a from your initial condition. All right, look back at the original problem. We were given the initial condition of 8, 0. That means everything is going to be measured, the area, because remember, an antiderivative, an integral, means the area starting somewhere. And we have to start at the number 8. So I want you to take that a out and replace it with the number 8. Now, how are you going to find c? Well, to find c, we're going to plug in the initial condition that we have, which is 8, 0. So where does the 0 go? No, the 0 goes for y. And the x, 8 goes for x, again at the top. Oops, and I forgot the e. E to the x tan x dx plus c. And what is the integral from 8 to 8? 0. So what is c? 0. For this particular problem, c is 0.
Why was A put in for A?
Let me pause it a minute. Okay, the way you write your final answer would be y equals the integral. 8 will always be the starting point. X will not always be 8. X will sometimes in other situations will be other numbers. Okay, but 8 will always be the starting point. E to the x tan x dx, and c happened to be 0 in this particular situation. Other times, x will be, the upper bound will be different. You might be asked to go farther away from 8, but 8 is always the starting position.
8 is always the starting position.
For this problem. Right.
Because
if there was a part B that said, now evaluate the problem when x is 10, then it would go from 8 to 10.
Okay, but then C will always be 1.
C is still 0. C is 0 for this function.
But what about other?
Okay, we'll do another one. Solve for y, and implied in that is also c, given -3, 4. All right, we are given dy dx equals the square root of 3 minus cos x. So don't overthink it too much. Solve for y. Well, what do I have to move first? Dx. Okay, that is called the separate step. Okay, separate your variables. Next comes the integrate step. That is those two steps, separate and integrate, you're going to do in repeated problems all through chapter 7. Okay, separate is always the first step, integrate is always the second step. So we separated, now we're going to integrate. All right, separate, integrate. Now, that gives me y by itself. What will the lower bound of this expression be? -3. The upper bound is x of the square root of 3 minus cos x dx. So this problem is orientating area beginning at -3. Plus, there's some c value that I'm starting with. Okay, to find our c value, we're going to use all of the initial condition, which is -3, 4. So 4 goes in for y. The integral is going from -3 to -3, which is automatically always 0. Oops. Plus c, so c would be 4. Okay, I was just going to ask you the same thing. Okay, yes, c is always going to, if you set your lower bound as the x value, c will always turn out to be the y value. So, yeah, so you can skip that step if you like. Okay, I have no problem with that. You can go, I'm going to erase this stuff that I just did, and you can just, I was just trying to prove to you why that always worked. Okay, so we can say that c would be plus 4. Now, eventually, you'll learn how to finish that integral. Right now, you don't know that yet, so we're stopping here at this point.
Oh, so we would
Okay?
have an answer, like a number?
Yeah, so you could actually have a number. Okay? You could actually get a number with your calculator at this point. If I said, okay, then what would the answer if x is 2 be? You could use a calculator, plug x to be 2 in your upper bound, and have an FN int figured out for you. Okay, that would work. If you did that, what would the answer represent? What would it, yeah, like if you plugged 2 into your upper bound, you did FN int, and it came out to be 13.491. What would that mean? The area from is 13.491, right? So you can do it with your calculator. Eventually, you're going to learn how to do it all by hand, how to find the antiderivative of that, and then be able to do that by hand. We just haven't gotten that far yet. How to do something of an antiderivative that has a square root and a cosine. Like you can do just a square root, and you can do just a cosine, but so far you don't know how to do a square root and a cosine. And in the previous problem, you could do an e to the x by itself, but you haven't even learned how to do tan x by itself yet.
Is it hard?
No, you just haven't learned it yet. Okay, it's not that it's hard, you just haven't learned it yet. Once you learn it, it'll be fine.
I'm ready.
Okay, so yes, to summarize, this -3, 4 is always going to be in those, that always show up in those two positions. It will be your lower bound and it will be your plus c. Okay, last example. Solve for k. Integral 0 to k of the natural log of x dx equals 5. All right, we want to solve for k. K is one of my upper bounds. This is where you're going to use your calculator. I've showed you how to do this one time before. I'm going to show you again. This is going to be a calculator-dependent problem. The front half is going to go into y1. The number 5 will go into y2. And you simply find the intersection. And the intersection will tell you what the k value would be on that integral to guarantee an area value of 5. So we're going to switch over to our calculator to finish this up, and then that's it, all that you need for the weekend.